Hello everyone, myself Sakshi Mittal. Today I am going to discuss about my third lecture for subject KEC 062 Satellite Communication. In this lecture, we are going to discuss about satellite link design. In my previous lecture, I have discussed about the orbital elements and I have discussed these 6 major elements like the eccentricity, semi-major axis, right ascension of ascending node, inclination, argument of perigee, time of perigee passage. So, you can refer my last lecture to know about these elements, as we have already known that if I want to know the location of a satellite, then how can I locate the position of a satellite by having the exact knowledge about these orbital elements, or you can say that if you have the knowledge about the look angles, that is your elevation, azimuth angle, then you can locate the position of satellite correctly. So now, as in this lecture, I am going to discuss about the link design, that I have to establish a link between a Earth station and the satellite, and again back to the Earth station. So if I have a mismatch in any of these elements, then I will not be able to establish a proper link from the Earth station to the satellite, and then from satellite back to the Earth station. That means if my satellite's antenna, it is pointed correctly towards the Earth station, then it is in my communication range. But if it is not pointed towards my Earth station and it is pointed out, let's say, at some other Earth station, then I will not be able to have a proper link. So to establish a proper link, first thing that is necessary is the knowledge of these orbital elements. So we have already discussed about these elements. So now I'll start from the satellite link design. So satellite link is defined as an Earth station to satellite, then from satellite to the Earth station connection. So when I'm having a connection from Earth station to the satellite segment, we call it as a uplink, that I am transmitting information upward. And when I have a link from the satellite towards the Earth station segment, we call it as a downlink, that is, we are receiving the information at the Earth station. So my Earth station design, it consists of two things: the transmission link design, or we say the link budget, and the transmission system design. So the first thing is the transmission link design, that if I have to establish a link, that is, from if I want to transmit any information at the ground Earth station, what all components I require? I require a system. I want a system which can encode my information, then which can modulate my information. It will then transmit it towards the satellite. Then satellite, I have some regenerators, or I can say some repeaters. It will repeat the information, it will regenerate the information, and after that it will be broadcasted towards the ground Earth stations. So I need to establish a link, or I want to calculate I want to have a proper link budget for this purpose. So the link budget establishes the resources needed. So whatever resources are needed for a given service to achieve the performance objectives, we call it as a link budget. Considering all the parameters like your atmospheric effect and the distance, at how much distance you have your satellite, if you have placed it in a low Earth orbit or you have placed it in a geostationary orbit. So all the factors we will be seeing. Now there are the 4 factors related to a satellite system design. See, the 4 factors, if I want to know about the satellite system design, first thing is the weight of a satellite. What is your application? So your application will define the weight of a satellite. If for example, you want to have a satellite only which generally have a camera on it. So you just want to click the pictures of particular land area. So the most important thing is the weight of a satellite, because in that case you are going to launch it maybe in a low Earth orbit. So you don't want to have more application for that particular satellite. So I want that the weight of satellite should be limited. Otherwise, it will increase my cost. It will be difficult for me to place the heavy satellite into the orbit. So the first factor is the weight of satellite. Then the choice of frequency band, on which frequency band you want to operate, that your satellite must operate. Then the atmospheric propagation effects. So the third is the atmospheric propagation effects. Whenever we are launching a satellite, we must know all the atmospheric effects that can play a major role while having a communication link between a satellite and a ground station. And the last one is the multiple access technique. uh, or which technique you are using. You are using the frequency division multiplexes, or you're transmitting your data like with the help of a TDMA, time division multiplexes. So the major frequency bands that I use generally, as I have already illustrated in my previous lecture, that the major frequency bands, we are generally using the C band for satellite communication. You can use Ku or Ka bands also. So the major frequency bands are 6 by 4 gigahertz, 1411 gigahertz, or 3020 gigahertz. So wherever we have mentioned the two frequencies, it's not that if you have to divide it and you'll get to some number. It just that the first frequency represents the uplink frequency and the second one represents the downlink frequency. As we are already aware that this uplink and the downlink frequency are different to avoid any kinds of interference. So we can have these three common frequency bands. Then at the geostationary orbit, there is already satellite using both 6 by 4 and the 14 by 11 gigahertz. So every 2 degree, that is, it is the minimum distance, it is the minimum separation. So to avoid any kinds of interference from the uplink Earth station, you should have a minimum of 2 degree space between them. So this is the satellite link design. Or what is a link? Link is nothing but is a connection between any two entities. So if I am having a ground earth station and a satellite, so the link between them is my uplink or the path on which you are transmitting your data. So this picture, it illustrates the maritime system, satellite system using a geostationary satellite. So you can first see here in the, we are having here like I'm having the gateway earth station. It is my gateway earth station. First, it will transmit the information to the satellite. This link, we call this link as the uplink. Then satellite, it will transmit the information back to your earth station, so to the ground. It can be your ship, it can be your aircraft. So this gateway earth station, it already have a connection to your terrestrial network. So these links we want to deal about we have to establish these links. So we need to study if I am transmitting the information, then whether the complete information will reach my receivers or at the destination point, or my information, whatever information the satellite will be transmitting to the ground earth station, will it be corrupted by any kind of atmospheric noise, or it will be transmitted as it is. So we need to study all these factors. So the ships are generally equipped with your steerable gyro stabilized antennas, and aircraft has your phased array antennas. So in this, generally it is nothing, it is but a maritime satellite link. We are showing that you have a gateway earth station which is communicating to a satellite. Satellite is in back communicating with your ships or the aircraft using L-band links. Now the RF satellite link design, the RF carrier in any microwave communication link, it begins at the transmitting electronics and propagates from the transmitting antenna through the medium of free space and absorptive atmosphere to the receiving antenna, where it is recovered by the receiving electronics. So at the ground earth station, you have some electronic part. Obviously, you have some electronics part which will transmit your data with the help of antenna. And it will, from how, if you have transmitted your data, what is the path? It is nothing but is the free space. Then at the satellite, it will be received by something. What is that? It is some electronics part. So that it will again, that receiving antenna, it has recovered the data with the help of some electronics. Now the carrier is modulated by a baseband signal that transfers the information for the particular application. So when you are transmitting your information, I have some data on the ground earth station, but I cannot transmit my information as it is. I have to encode it for authentication purpose. Secondly, I have to modulate my data. And so if you have to modulate your data, then you need a carrier. So the second point tells about this, that the carrier is modulated by a baseband signal, that is your message signal, which will transfer your information for the particular application. So the first step is to identify the overall requirement and the critical component that determine your performance. So for this, we have a system link like this diagram. It shows how whatever connections, what all components or what all electronic components are required for transmission from the earth station, then from the satellite back to the earth station. So first is here, information input. I have my message signal here. I have some data. I want to transmit it to the satellite. So I cannot transmit this information as it is. Firstly, my data will be encoded. You can apply any encoding techniques to maintain the authentication of your data so that any unauthorized user cannot access your data. Then you will modulate it. Now, after modulation, we generally have the data in the form of, let's say, in kilohertz. So I want to up convert it because satellite links, they are generally established in gigahertz. So I want to up convert my frequency. Then after up conversion, we have a high power amplifier. So at the ground earth station, we have got a high power amplifier. After it is in the now gigahertz band. You have already amplified it. The data will be transmitted with the help of this antenna. Now it has transmitted the antenna, it has reached the satellite link. Now satellite have received the data. Now satellite want to retransmit this information back to the earth station, or maybe it want to distribute this information to various earth station. So satellite repeater will regenerate the information and it will transmit this information. Now this information will be redistributed to various earth stations. If it is a broadcast application, or if it is point to point application, then from A to satellite and from satellite to another destination, maybe B. So on the receiver side, you first have a low noise block converter. First of all, when you have received the data, you must suppress the noise. After that, you have to demodulate the data because you have already sent the modulated data. Just demodulate the data, extract the message signal and then decode it, because after decoding only you will get the information which you have sent from the ground earth station. So this information output, it must be same as the information input. So these are all the electronics part which are involved in transmission or reception of your data. So now the consideration for satellite link design. Free space attenuation, it is determined by the inverse square law, which states that the power received is inversely proportional to the square of distance. Now see, if I am transmitting a data, let's say at very long distance. So if I am transmitting at very long distance, the power, it will obviously at very long distance the power will decrease. But if I am transmitting for a short distance, it will have the high power. So that means we can say that the power received, it varies inversely with the distance. As you are transmitting data to a very far distance, power will be low, otherwise you will have a high power signal. Then the number of additional effects that produce a significant amount of degradation. So the and your time variation, you have to also incorporate these, like additional effects. You can have the atmospheric effects, you can have the losses associated with the antenna. So first thing is the free space attenuation, because the path is the free space, so you have to consider this. Then we know that the second my parameter is the distance. If I am transmitting at a long distance, power will decrease. Then we can have the consideration of the additional effects that produce a significant amount of degradation and time variation. Then these majorly include rain, terrain effects such as absorption by trees, falls, some less obvious impairment produced by unstable conditions of the air and ionosphere. The required factor includes the performance of satellite itself, because there can be the losses associated with the satellite receiving antenna. The configuration and the performance of uplink and downlink earth station, it is also another factor, and the impact of propagation medium in the frequency band of interest, whichever band you have chosen. So what impact that have on the propagation medium. Next things to consider is the bidirectional communication. There is a duplex or the two-way communication. It occurs with a separate transmission from each earth station. Generally on the earth station, I want to transmit information, and the earth station, it want to receive information from satellite also. So the antennas which we use at the earth station, they are generally the duplex antennas, or we can say the duplexer. The same antenna will be used for transmission as well as the reception purpose. Now, due to the analog nature of the radio frequency link, each element contributes a gain or loss to the link and may add noise and interference as well. Like I have already mentioned, there can be the losses associated with the transmitting antenna and the receiving antenna. The result in the overall performance is presented in terms of ratio of carrier to noise power and ultimately the information quality. So any uncertainty can be covered by providing an appropriate amount of link margin So if you have a link margin which is over and above this carrier to noise ratio, so that you can deal with the propagation effects and all the other non-linearities in the earth station and the satellite repeater. So you have to design a link such that the C by N ratio, that is your carrier to noise ratio, it is maintained, considering all the factors like your propagation effect, your non-linearity in the earth station, satellite repeater, your losses, your path losses, and etc. So my service quality, it depends on the bit error rate, and again what I want to do, I want to maintain the carrier to noise ratio. So it depends on all the parameters like your EIRP, that is your gain and the relation combination of your power and gain of the antenna. Then the receiving antenna gain, free space losses, you can have waveguide losses, atmospheric losses, rain attenuation, you can have tracking errors. Then the interference, you can have a co-channel interference, you can have some noise, thermal noise, uplink thermal noise, downlink thermal noise. So coming to the satellite link budget. Link budget is a set of calculation giving the feasibility and performance summary of a particular communication link from the transmitter to the receiving end. So the link budget determines the antenna size to deploy, or what all other things it can deploy, like the power requirement, your link availability, your bit error rate, overall customer satisfaction with the satellite service. Because you have already placed a satellite, you have already launched the satellite into its correct orbit. Why you have placed the satellite? You are basically dealing with its orbital elements, you are checking the position of that satellite. But you in the satellite subsystems, you have checked the health of satellite also. But the major concern is whether it is fulfilling the task for which I have launched it, whether it is performing the as per the application. So the overall customer satisfaction with the satellite service is also plays an important role. So link budget is a tabular method for evaluating the power received and the noise ratio in a radio link. The link budget, it must be calculated for an individual transponder and must be recalculated for each of the individual link. So see, carrier to noise ratio, this calculation is simplified by the use of link budgets. The evaluation of received power and noise power in the radio link. The link budget must be calculated for individual transponder and for each and every link. When you are employing a bent type transponder, we generally have two types of transponder, a bent pipe transponder and a regenerative transponder. In case of bent pipe transponder, it is like a pipe, a bent pipe from where you have given something from one side and from the other side the water flows out. So if I have given something, so this bent pipe transponder, it will only perform the function of frequency conversion. It will not perform any other function. So if I have a transponder of this type, we call it as a bent pipe. On the other hand, I have a regenerative transponder which generally performs all the functions which your repeater performs. So it will get the information, it will demodulate it, it will decode it, then you will get the information. And while transmitting, it will do each and everything required. It will not just frequency convert the data. So when a bent pipe transponder is used, the uplink and downlink C by N ratios must be combined to give an overall C by N. That is your carrier to noise ratio. So we can combine both the uplink and downlink C by N ratios. Now satellite link design methodology. So the design methodology for one-way satellite communication link, like for establishing the second link, that is from satellite to the earth station, you can again repeat the same process. They can be summarized onto the following steps. The steps are like this return link, it follows the same procedure. So my step 1, frequency band determination. First select the band in which you want to launch, in which you want your satellite to operate. You want to operate it in C band, L band, or whichever band you want to operate it. Next is satellite communication parameters determination. Make informed guesses for the unknown value. You must know about every parameter. Then the earth station parameter determination, both uplink and downlink. Then establish a link budget, uplink budget, because you're transmitting information from earth station to the satellite. So I am concerned only about this link budget, that is from station to the satellite. And a transponder noise power budget to find the carrier to noise power in the transponder. Then determine the transponder output power from its gain or output back off. Whatever information is back off in your output, you must first determine the transponder output power. Then establish a downlink power and noise budget. So this was for the first step. First 1 to 5 steps we have generally considered from the earth station to the satellite. Now we are considering for the downlink, that is from the satellite to the earth station. So establish a downlink power and noise budget for the receiving earth station. Then calculate your C by N downs for, you have to calculate your carrier to noise ratio once for your uplink, then for your downlink, and after that you can just combine them. So calculate the signal to noise ratio in the baseband channel. Determine your link margin. So how much margin we have to maintain the proper carrier to noise ratio. Then do a comparative analysis of the result. Then tweak the parameters to obtain the acceptable value, how much value you want. Propagation condition determination. So if your signal traverses through the space, what are the propagation conditions? So you must determine those conditions. Uplink and downlink unavailability estimation. So maybe the link is not available. Whenever you transmit information from the earth station to the satellite, so satellite generally repeats or it retransmits the same information back to the earth station. When earth station receives the same information, it got to know that the satellite is available, then it will transmit the information which it want to transmit. Or you can say it in simple word, like we say hello. So first packet that earth station has sent to the satellite is the hello packet. Once satellite has received the hello packet, it will again retransmit the same information hello to the ground station. Now it has again received the same packet hello. Now it knows that the satellite is available, or you can say the satellite is ready to receive your data. So in the next TDM slot, you can transmit your information. So that means by this procedure, we have established whether this uplink or downlinks, they are available or not. So their unavailability estimation. Then redesign system by changing some parameters if the link margins are inadequate. Then whatever the parameters you have calculated, are they reasonable? Is the design financially feasible? If yes, then it's perfect. You have designed the satellite link is successful and you can just stop it now. But if you got no for any of the answer in the step 15, then the satellite link design is unsuccessful. So you have to start the procedure right from the step 1. So now we have just discussed about all considerations we must have for designing the satellite link. Now we'll just calculate. So we'll start with the basic transmission theory. So the calculation of power received by an earth station from a satellite transmitter is the fundamental for the understanding of a satellite communication. So there are two approaches. First is the use of flux density and the link equation. So we have to derive the link equation and with the help of this flux density. So we'll calculate the flux density. We have assumed isotropic source. This is my isotropic source. Isotropic means it will radiate uniformly in all direction. So we say that the effective isotropic radiated power is generally IPT, is the isotropic antenna, so gain is 1. So it is PT watts. And I am going to measure the flux density at a distance r meter. So see, this area, it is actually a meter square. The flux density of this receiver will be F watt per meter square. When the isotropic antenna, it is radiating uniformly in all direction. So the receiver, how the radiation pattern will be? It will be spherical. The radiation pattern will be spherical when it is radiating uniformly in all direction. So that means this area which we are considering here, it is nothing but the area of a sphere. So at a distance r, the flux density, how we'll calculate the flux density? Flux density will be the power received by per unit area. So power received is the PR and per unit area of your sphere. So the area of sphere is your 4 pi r square, watt per meter square. So this was for the isotropic antenna. So for isotropic antenna, you have the power per unit area, that is PR by 4 pi r square. So if I consider the directional antenna, so for directional antenna, I'll have it like PT GT by 4 pi r square. GT is the gain of your transmitting antenna. So if because ideally it is possible that you can have an isotropic source of antenna, but in reality you don't have, because if you have an antenna, it will obviously have more radiation, it have more intensity to the elements which are in front of it. It will not radiate uniformly in real situation. Now this PTGT, it is known as EIRP, that is your effective isotropically radiated power. It is nothing but the combination of your transmitter power and the antenna gain. Now we'll calculate the received power. So see, we have calculated the flux density. Now my received power, it depends on the aperture of my antenna, because if you have radiated some power, and how much power my antenna will collect, it depends on its capability. So I can say that the flux density, that or we can say the received power is flux density multiplied by the area. So this is the flux density, PTGT by 4 pi r square. Now you can multiply it with the area to have your receive power. But what about the area? Area is my aperture area. Aperture, the complete aperture is not generally involved in capturing the data. We say we have an effective aperture. Effective aperture or the effective area of that antenna, it depends on its efficiency. Generally, your horn antenna has the efficiency of 90%. So we say that the effective area is nothing but the efficiency into that total area of aperture. So we can write this like the receive power is flux density multiplied with the area or the effective area. So flux density was PTGT by 4 pi r square multiplied with the effective area. And this effective area is nothing but depends on the efficiency multiplied with the total area. So this PTGT AE by 4 pi r square. Now we have the relation between the gain. From the antenna theory, we have a relation between the gain and the area of antenna, which says G is 4 pi effective area divided by lambda square. So if I can replace the value of this effective area in the previous equation, we'll got it as PR equals to PT GT GR by 4 pi R by lambda square. So this is the received power in terms where PT is my transmitted power, GT is the gain of transmitting antenna, GR is the gain of receiving antenna, R is the distance at which you are transmitting, at which you are calculating your flux density or your received power. And the lambda, it depends on the frequency band which you have used. So this equation, this is known as your link equation. PR equals to PT GT GR by 4 pi R by lambda square. It is my link equation. So it is essential in the calculation of power received in any radio link. The frequency, or I can say the wavelength, it appears in this equation for the received power because we have used the receiving antenna gain instead of effective area. Now this denominator part, 4 pi r by lambda whole square, we call this term as a path loss. If it is not a loss in the sense of power being absorbed, it accounts for the way the energy spreads out as the EM wave travels from a transmitting source in your three-dimensional space. So collecting the various factors, we can write it as like PR is EIRP, that is PTGT EIRP multiplied by receiving antenna gain, that is your GR, divided by path loss. This expression, or we can say the link equation, it was in watts. If I convert it in decibels, so the received power in decibel watt, it will be EIRP plus the gain of receiving antenna minus path loss. So this complete equation is now in decibel watt. So EIRP is nothing but you have converted this PTGT in decibel watt. Again, you have converted the gain in decibel, so you got this as GR. And path loss, you can calculate the path loss as 10 log 4 pi r by lambda whole square. It is equals to 20 log 4 pi r by lambda in decibels. If you have got your power, let's say in milliwatts, so that time at that particular case, your unit will not be decibel watt. Instead, it will be dBm. So I can write this equation, link equation as PR equals to EIRP. EIRP is nothing but PTGT plus GR, gain of receiving antenna, minus path loss. So we have considered other losses as well. That is LP is the path loss. Then LA is attenuation in the atmosphere. LTA, losses associated with the transmitting antenna. LRA, losses associated with the receive antenna. So when while you have transmitted the information in the free space, when it is propagating from the free space, these losses can account in for the data. So we have considered all these losses. So the link equation is nothing but it is the combination of your EIRP, gain and the losses. So this was all about the satellite link design. We have discussed what all are the requirements for the satellite link establishment, then it's for the link budget, and how we can just drive the formula for the link equation. These are the references which I have used for preparation of these slides. Pratt for satellite communication and D. Roddy satellite communication. Thank you.